of 40 minutes, we'll have 5 minutes of question and answer session, and then the next speaker takes over. So this is how we will proceed. So our first speaker for the day and for the conference is Professor J. Srinivasan from the Divecha Center for Climate Change, Indian Institute of Science, Bangalore. And it's very pertinent to recall that Professor Vasudeva Murthy did his PhD under the supervision of Professor J. Srinivasan. The title of his talk is an account of the exploration of the lifted minimum phenomena by Professor Vasudeva Murthy. Professor J. Srinivasan, the floor is yours.
Thank you. Can you hear me?
Yes, we can hear you.
Is my slide visible? The slide?
Yes, it's visible. Yes.
Okay, thank you. So let me thank TIFR for inviting me to talk about the work of Professor Vasudeva Murthy for his PhD. This was done along with Professor Rodham Narasimha, and this was done more than 35 years ago. And so some of this may seem a little outdated, but I want you to appreciate the condition in which this work was done. At that time, the computational power we had was somewhat limited. So one had to be very clever in trying to come up with a technique to solve some of these problems. Okay. The slide is not moving. Yeah. Now, what I'm going to say has already been written up by Professor Vasudeva Murthy. Last year, in January or so, Vasudeva Murthy wrote a wonderful tribute to Professor Rodham Narasimha, because Rodham Narasimha was he was a great admirer of Narasimha's achievements. And so he wrote a tribute in the International Center for Theoretical Studies newsletter. And he highlighted his experience with Professor Rodham while doing his PhD. Okay, so most of what I'm going to say is available in this write-up. You can look it up in the ICTS website. Now, let me first say what is the lifted minimum phenomena. Okay, and normally on clear nights, the Earth's surface cools very rapidly. And because the ground emissivity, the ability to emit radiation, is very good, while atmosphere has only a few molecules which can radiate. They are water vapor, carbon dioxide, methane, and so on. So on a normal night, clear night, the ground cools very rapidly, and the temperature of the ground becomes much lower than the air above it. Okay, and this causes what is called inversion. But on certain nights, when the wind is not high, it's calm, it was observed that air was cooler than the surface. It was not common, it was maybe once in a year. And this was discovered more than 90 years ago in 1932. And when this was discovered, people didn't believe it because this is such a rare phenomenon. So here is a sketch showing the in dashed line the normal temperature at night, and the solid line is on nights when the temperature lowest is not at the ground but a few centimeters above it. Okay, this was discovered first by Dr. Ramdas of the India Meteorology Department, and when this was discovered, people still had doubts about whether, because it was first discovered in India, not in any other country, and it was a very rare phenomena. So questions were posed about whether it is real, and if so, what is the cause? Now, this was published in German, India, 1932, and I must tell you that Ramdas was a very meticulous scientist. He was trained by Sir C.V. Raman, the Nobel laureate, and the measurement of temperature outside is not a simple matter. You have to ensure that you are measuring the air temperature and make sure that the instrument used measurement is shielded from the sky, because if you allow the instrument to radiate to space, then you're not measuring the local temperature. So all these things Dr. Ramdas was quite aware of. And so this work was discussed a lot. And in the here is a first observation made in 1931, both in Pune and Agra. You can see that the temperature at about 1 meter height is about a degree Kelvin below the ground temperature, okay, in two different locations, Agra and Pune. Subsequently, he made many more measurements where he got even a deeper temperature drop of about 2 to 3 degrees. And so he was able to show that this happens at least a couple of times a year in winter, and the sky is clear. Now, this was continued with, along with K.R. Ramanathan, another famous scientist. And the reason I show this picture is to highlight the fact that the air temperature very close to the ground compared to ground temperature, there's a sharp drop, okay, which is seen when you show data up to 1 meter or so. And this is sometimes called the radiation slip. See, the normal assumption we all make in engineering is that the air in contact with the ground will have the same temperature as the ground. This is called the no-slip condition. That is, there is no temperature difference between the air molecule near at the ground and the ground itself. But when there is radiation, there can be a slip of the order of at least few degrees. That's what this thing showed. Now, this is because in conduction heat transfer, which is where normally people say no slip, the mean free path of the molecule is around 60 nanometers. And it is so small compared to the scales in which make observation that we cannot see the slip at all. Okay? But when you deal with radiation heat transfer, you have to worry about the photon mean free path. The photon mean free path can vary a lot. And in the Earth's atmosphere, photon mean free path can be anywhere from 1 millimeter to 1 kilometer, depending on the wavelength you are looking at. So this is what makes radiation transfer more complicated than conduction, that simultaneously the photons can have very short and very long mean free path. Okay. Now, this work of Ramdas was discussed a lot in the famous book by Rudolf Geiger called Climate Near the Ground. So not many people work in the layer very close to the ground, and Ramdas did this work because he was working in the area of agriculture and meteorology. You would like to know what are the temperature of the crops close to the ground, and especially in winter condition, you don't want frost or ice to form on the, let's say, a tomato crop. Now, Geiger discussed this work in great depth, and one of the doubts many people had is that the cold air near the ground may be due to cold air coming down a slope. If there's a slight slope in the area, then cold air will start moving from some other point to a given point where you're measuring. And so the cold air you see may not be local. But Ramdas took a lot of care to make sure that he was in an area where it's completely horizontal. So he was able to show that it is not playing a role. Then there was a question of role of turbulent diffusion. Now, turbulent diffusion can have very complicated variation, but one can show that turbulent diffusion will destroy this minimum because it will mix the air very quickly. And this was shown by one of the colleagues of Geiger called Raschke. Yes?
PD.
Hello? Is there any problem? Can I continue?
There's no problem, sir. You can continue.
Okay.
There will be
So,
undisturbed 40 minutes. So there's no problem.
Yeah. So Geiger sent his colleague Raschke to India because he was very keen on checking these observations. He came to India and made measurements in Pune. And while doing that, he did a very nice experiment in which he took a piece of stick and waved it in front of the measurement device, and the minimum disappeared. So he showed that even minor disturbance kills the minimum. So turbulence cannot play a role. Okay. So now that this was confirmed that it was not an accident of measurement, a lot of people wanted to understand how to model it. Now, if you ignore turbulent diffusion, the basic equation governing this problem is the transient term on the left, the molecular diffusion term, which all of you know, and the radiative divergence term. Now, the radiative divergence term involves integration over wavelength. That is the trickiest part. And this is the flux, radiative flux given here, in which the angular integration is incorporated in the exponential integral function En. And the spatial integration is here from surface to the top of the atmosphere. And so the problem in radiation is complicated by the fact that you have to worry about angular integration, spatial integration, and wavelength. There are three dimensions to the problem: spectral, spatial, and angular. So that's what makes it up. But in this problem, one can treat angular somewhat casually because it's not that difficult problem. But the spectral part is very difficult. Now, this problem had been looked at earlier, and the most famous example is the work of Subramanian Chandrasekhar. So more than 8 years ago, he did a lot of work and published a book in 1950 called Radiative Transfer. In this book, he ignored the wavelength variation because he was looking at stars where the gas was a plasma, not like a neutral gas on Earth. So if the gas is a plasma, then it can absorb radiation at all wavelengths. So a gray gas, that is the spectral absorption coefficient, being independent of wavelength, this quantity being independent, is a good assumption. So when you do that, this problem is solvable. And the contribution of Chandrasekhar was he solved this problem 8 years ago without access to any computers. And so that work is well known. And but today, the problem we are dealing with is one in which you can't assume a gray gas. So our main challenge is that we have to take into account the spectral variation. Okay, so the problem solved by Chandrasekhar is shown here, and I just want you to look at the four terms that play a role: the emission from the ground, emission from the top, and emission by all layers above and below a given layer. All these play a role, and Chandrasekhar accounted for that quite nicely in a gray gas, where spectral variation is not there. And it is a very useful result for astrophysics. But in the Earth's atmosphere, dealing with a neutral molecule, and there the absorption emission is occurring due to vibrational transition. The vibrations of water vapor molecule will result in photons being absorbed, emitted. And in addition, rotation of the molecules also will contribute. So this is called the vibration rotation band. They occur together. Okay, and it's a very complex spectrum. I want to give you an impression of how messy the problem is. And so this is the modes of vibration of the water vapor molecule, and we will focus on this bending mode, which is the one which absorbs radiation and emits radiation around 6 micron, where the Earth's emission is quite high. Now, the complexity occurs because rotation and vibration occur together, and there are lots of lines, thousands and millions of lines which are there. And here I've shown you the absorption coefficient of water vapor, that is light blue, along with carbon dioxide, the second most important gas, which is in dark blue. You can see that in most of the spectrum going from 4 micron to almost 50 micron, water vapor dominates. Only in few places, like around 15 micron and around 4 micron, carbon dioxide has a role. So the focus that we will have is primarily on water vapor because it dominates the absorption emission near the ground. If you look at the whole atmosphere, then CO2 is equally important, but near the ground, CO2 is not that important. Now, here is the comparison between water vapor and carbon dioxide absorption. You can see that water vapor absorbs in many wavelengths, while carbon dioxide absorbs in a few wavelengths. Carbon dioxide is a linear triatomic molecule, while water vapor is a nonlinear molecule. Water vapor is a more complex molecule that we have to deal with. Now, typically in a textbook, if you see the transmission through water vapor is shown as a nice, simple, smooth curve. But this is completely misleading. This is not the true picture. The true picture is here. This is how the absorption coefficient or transmission of water vapor varies with wavelength between 4 micron to 30 micron. And you can see that the vertical lines, the transmission goes from 0 to 1 in a very short wavelength range. So if you want to integrate across wavelength, then you have to use a very fine spectral interval to ensure that you capture the sharp variation of the absorption line. Okay, so this has been a problem for a long time. Now, when Vasudeva started his work, you must remember that our computational power was limited, and also the data of water vapor absorption also was not very high. Today, the situation has improved a lot, so one can do a more sophisticated technique. But I'm going to talk about what Vasudeva dealt with. Now, each of these lines has a structure, and the shape of this is called the Lorentz shape, which is a Gaussian, and this comes about because the collision of nitrogen and oxygen molecules with water vapor molecules. And the challenge is that at the middle of this Gaussian here, absorption is very strong. It rapidly declines, and then again it rises in the next line. So, so there is very little absorption here and very strong absorption there, and you have to take care of all the lines. Now, the original model proposed by Althusser had equally spaced lines, infinite of them. But for water vapor, people realized that the spectral absorption is so complicated that you are better off using random line model. Okay, so both have been tried. Now, the fact that there are so many lines and each line decays slowly as it goes away from the center of that wavelength. Here is a picture of the absorption coefficient of water vapor. I'm going to focus on 3 locations. One, the vibrating rotation band, here very high absorption, around 6.3 micron, and then another long absorption thing in pure rotation band of water vapor. In between, there is a minima, which is called the window, because absorption is very small. Notice that absorption here is about 1,000th, or sorry, 1 by 10,000 of what is there here, okay, or even 1 by million of this. So there's a very weak absorption here, and there's a very strong absorption there. But we need to model this weak absorption also, because this is where the Earth radiation is able to cool to space through this window. Okay, so even that has to be handled very carefully. So to summarize, the spectral absorption band of water is very complicated. There are 3 things. One is the vapor rotation band at 6.3, and a rotational line going by 16 all the way to 40 to even 100. And in between, there is what is called water vapor continuum. That is a weak absorption between the 2 bands. Okay. Now, interestingly, even today, there is no universally accepted physical model for this absorption. It is assumed to be due to hundreds and thousands of lines, their tails coming together near 10 micron, and although each one contributes very small, the sum of this is not negligible. Now, the first thing that Vasudeva tried is a model in which you assume that either photons are absorbed very strongly, as in the 6.3 micron band. This is called the thick limit. That is, the absorption coefficient times the length scale is very high. Okay. And then diffusion kind of approach is valid. So then you can add the diffusion through photons to the diffusion by molecules. So this model was proposed by Kuo more than 50 years ago. Then the second term is to do with cooling through that low absorption region near 10 micron. This is called Newtonian cooling, the thin limit, where absorption is very weak. Okay, this was an elegant approach, but after trying to solve this problem, he had some difficulty. Then he used his knowledge of mathematics to show that without solving this equation, he showed analytically that these equations cannot produce a minima in the interior. This was an elegant piece of proof that this solution with that boundary condition at the ground, which is the observed boundary condition, cannot produce a minima. Now, this unfortunately was not published. It is in his thesis, but he has not published it, which he should have published it. He thought it was too simple to publish. But I thought it is an elegant way to demonstrate without solving the equation that one should not waste time solving the equation, because it does not cannot produce minima in the interior. So then we went to the next approach, which is called the emissivity model. In the emissivity model, we avoid the whole complexity of integrating the equation with wavelength by trying to use laboratory data of emission of water vapor. Okay. Now, so emissivity is defined as follows: 1 minus e to the power minus absorption coefficient times the path length of water vapor times the Planck's black body function. This is a well-known definition of emissivity. And the path length is nothing but the total amount of water vapor in the vertical. It is given a symbol U here. And so this is an integration in wavelength, which we cannot do because of the complexity of the bands. But we can go to the laboratory and measure this quantity. Okay, so this has been done. And so here is data showing how emissivity of water vapor varies with path length from 0 to 10 kg per meter squared. But our interest is in the region very close to the origin, because we are very close to the ground. So our path length is very, very small, somewhere here. Okay, so near the ground, there's a sharp variation, and then it's is logarithmic. So this is fitted by two equation, and so this is what Vasudeva did, and we have confirmed that this emissivity model agrees well with experimental observation by Corradini and Severini in 1975. Okay, so this is a theoretical model supported by observation from laboratory in a length scale relevant to this problem, which is of the order of meters. Now, this is the equation for fluxes downward and upward, and you can see the flux depends on the derivative of the emissivity. So one has to correctly get the derivative correctly. Now we can non-dimensionalize the equations for convenience, and we can get many parameters like Boltzmann number, Reynolds number, in case you want to take into account the role of wind and so on. And there's a one length scale which emerges here, which is related to derivative of emissivity and density of water vapor. Okay, I'll come to the issue a little later. Now, this equation in the atmosphere, which has molecular conduction and radiation heat transfer, is solved along with the equation for the ground, that is the ground below the atmosphere, and this is the ground thermal conductivity. Okay, so you are solving for both air and ground simultaneously. That's a bit of a challenge because the response time of the ground is very slow, while the atmosphere is very fast. So one needs to carefully handle the numerical stability from that and control that. Okay. Now, just for your completeness, I'm giving you the grid sizes you use. Near the ground, you have to use very high resolution to capture the lifted minimum. But as you move away from the ground, you use somewhat cruder grid resolution. Okay. There are about 250 coupled equations solved by method of lines. If you're interested in the details, it's there in its thesis. Okay. Now, the observed temperature variation at the ground has been documented by many people. So, in the first part of the work, we fitted that ground temperature variation to a simple expression, which can be actually derived theoretically. Later part, of course, he solved both the ground and the air together. Now, here's the result he got, and I'm showing the result in two parts. One from 0 to about 35 meters, where the minima is very close to the ground, you cannot see it almost, which emerges after 1 or 2 hours after sunset. But as you see in the inset, that is the close-up of the lowest meter, and you can see a minima appears after about 1 or 2 hours, about 1 or 2 degrees below the ground temperature. So we're able to capture the occurrence of the minima. Okay. Now here is a close-up of the solution of the combined soil and air equations, and you can see that the crosses here are the solution in which we prescribe the ground temperature variation as given here, and the solid is the solution to the combined equation for air and soil, and one can say they agree quite well. Either you solve only for air with the given boundary condition transient, or solve the combined air and soil equation with the same answer. And the key point about this particular figure is when the ground emissivity is 1, you do not get a clear minima. Okay, the minima appears quite prominently only when you allow the emissivity to go below 1. This was a great surprise. This had not been talked about by anyone, because at the time when Ramdas and others made measurement, ground emissivity is not accurately measured. Today we have measurements of ground emissivity, and we know that ground emissivity can be anywhere from 0.8 to 1, depending on the ground geological, what kind of composition the ground has, and the wetness of the ground. So we varied the ground emissivity between 0.9 and 1, and found that the answer is very sensitive to ground emissivity. This was one of the major discoveries of Vasudeva Murthy. Okay, and here is one more example comparing his simulation with the original one of Ramanathan and Ramdas in 1935, and again showing that although the agreement is not perfect, it's quite good. Okay. Now, this radiation slip, that is the temperature drop very close to the ground, is sensitive to emissivity. You can see that if emissivity is 1, the slip is almost 0. There's no temperature drop. But as you reduce the emissivity, it goes up to 2 to 3 degrees. And if you're willing to go even lower values, can even have 6 degrees. Okay. In some deserts, you may even see 6 degrees because the desert soils have low emissivity. Okay. Now, Vasudeva Murthy looked at how this location of the minimum above the ground depends on the ground cooling rate. Okay. Ground cooling rate is simulated as follows. And you can see that if the ground cooling rate is very high, the minimum comes close to the ground. And if the ground cooling rate is very high, the minimum temperature goes down. And you can see that the emissivity is approaching 1. So he essentially mapped the entire parameter space of emissivity and cooling rate to show under what condition this lift middle occur. Okay. Now here is a graph showing again how sensitive the location of the minimum above the ground is to the emissivity. You can see it's almost around 30 centimeters above the ground, but as you approach 1, it rapidly drops to 0. Okay, so this is the phenomena which was unique to this role of emissivity of the ground. Okay, now he varied all the parameters that were available and showed how the minimum temperature depends upon location of minimum depends on all these parameters. And I will not go into the details of this. These are available in the paper. I will talk about the paper. I'll show you the paper very soon. Okay, and also the how strong the minima was depends on all the parameters that he explored. Okay. Now the question was, can we simulate the lift minimum without using emissivity model? Why? Because there have been a lot of critiques on the emissivity model. Remember, emissivity model is an empirical model based on laboratory data, and people felt by 1990s that we shouldn't use the model. You should use more sophisticated models available because of the ability to now integrate across wavelength with more data being available. So people, so Vasudeva Murthy was keen to see whether the same results can be simulated by a more complex model. So he worked with doctoral student Sai Varghese, who was a student of Professor Narasimha, and they used a band model. Band model is you divide the water vapor into 3 bands: the 6.3 micron band, the rotation band from 15 to 20 micron, and the continuum. And each region you fit a separate relationship between absorptivity and wavelength. And when he did that model and it was run, that model could not produce a large cooling, and hence did not produce a very strong lift minimum. Now the question was, why did the band model not produce that? The reason was these band models were developed for climate model being used today to look at the Earth's global warming. Okay. Now these climate models are there to look at the temperature of the atmosphere from about 1 meter to 100 kilometers. So they were not meant to be used close to the ground. So the kind of fitting that was done to the absorption coefficient were not correct for phenomena close to the ground. So it did not give the right result. Okay. Now, the reason why can we see in the next figure here. This is the transparence of water vapor with path length being fitted in a narrow spectral range. And you can see that the fit does not agree with a more accurate fitting of the line by line integration done much more accurately. And so as you go close to the ground means lower path length, the agreement is not good. So this is one of the problems with band models which has not yet been solved. Now, these band models sometimes now is getting more sophisticated. They divide the wavelength into 8 zones as shown here and try to get the absorption coefficient fitted correctly over narrow intervals of spectrum. So, so this is still going on, this kind of attempt. This is called line by line models, and but nobody has combined this with the solution of the type that Vasudeva Murthy attempted. And but even these models have problems. For example, here is an example of the comparison between a climate model which uses these kinds of model versus a line by line model which is more accurate. The difference you can see is quite high near the ground. Okay, and near the top of the point is okay, but near the ground there are large differences between the band model calculation used in climate models and the line by line integration which you can do, which cannot be used in a climate model, can be used offline separately. So there's still a problem with that which needs to be resolved. And as a matter of fact, Vasudeva Murthy was very keen to do that, and we were discussing that. Only that we didn't have sufficient computational power, but in the last few years, our computational power has gone up. And I was talking to Vasudeva Murthy about a plan to combine a line-by-line radiation code with solving the full radial transfer equation. And before I talk about that, let me just point out the paper that he published based on his doctoral work, which you can look at for more details. And finally, I want to answer a simple question about the Lifton minimum. After all, the paradox was, why is air temperature lower than the ground temperature when air is a poor emitter? Because air can emit radiation only through minor molecules like water vapor, carbon dioxide, ozone, and methane, and not through nitrogen and oxygen. So it is a poor emitter, while ground is a very good emitter. So the answer to that question is interesting. It is that the air which is cooling to space through the window region gains heat from the ground by radiation, and it does not gain much heat by conduction because air is a poor conductor. But the ground, which is a good emitter of radiation, also gains heat from below the ground by conduction. So we found that when the conductivity of the ground is large, which is true in many cases, the ground cannot cool rapidly, although it is a very good radiative emitter, because heat is transferred from below the ground to the ground quite rapidly. So the main reason why minima occurs at the region above the ground is in those regions where the ground conductivity is quite large. So this was not appreciated 80 years ago or 90 years ago. Everyone was focusing on radiation issues, which is important, but we must also worry about the way the ground is cooling. So if the ground cooling is not high because ground is getting heat from interior to the surface, then in certain special days, the air can cool faster than the ground. So essentially, minima occurs because the rate with which radiation emitted by the ground and absorbed by this minima is equal to the radiation emitted by this minima to the space. Okay, and this also explains why ground emissivity is so important. If the ground emissivity is below 1, then the ground emits less radiation to this minima location. So if emissivity is 1, it will kill the minima because it will radiate a lot of radiation to this thing. If you reduce emissivity, it is not able, the air is not able to absorb that much radiation from the ground. So that is the main story which emerged. So it is both the role played by radiation emitted by the atmosphere to space, as well as the role played by heat transfer from beneath the ground to the ground. Both played a role. And so that was what Vasudeva found out. But still, he was not satisfied. He still wanted to do a more sophisticated model, but he didn't get the time. Now, after retirement, he talked to me and he was hoping to use the line-by-line code, which is the most accurate code available today, along with solving the differential equation. But that did not happen because of his untimely demise. I hope that somebody else will take up this challenge of solving the line-by-line integration of the equation along with solving the differential equation for cooling of the air. Okay, I will stop here and I'll be ready to answer any questions. Thank you.